In this video, we want to look at a model of the spring force. The spring force is one of the more complicated models that we'll have of a force, and it's one of those that really defies a easy and universal mathematical description. And so I want to focus on a verbal representation of the spring force model and then be able to translate that to a mathematical representation depending on the particular problem that we have. So let's start with the what comprises the spring force model. Right. Our first element of our spring force is that our spring has zero mass. Okay. And the second is that it is in one-dimensional spring, and so it doesn't bend. So if I draw a spring here, so it of course stretches and compresses, but what it doesn't do is sort of bend that way or that way. It stays all in a one-dimensional orientation. Okay. So our third element of the spring force is that it doesn't break. That would be handy. And I think everyone realizes, if they've ever worked with a spring, that if you pull it too far, it stresses permanently, or it in fact breaks apart. And also, if you compress it too far, the coils come up next to each other, and you can't compress it any further without breaking it. And so essentially we're saying that we never achieve any of those regions. It never comes to this breaking point. Another way to think about that is we're in this regime of small oscillations, where we're stretching and compressing the spring a small amount from its natural length. Okay. So that's our third element. The next piece is that a spring in our model connects two objects. And that sort of has to be true. We'll have a spring has two ends, and so it necessarily connects two objects. Maybe one is holding onto someone's hand, maybe one end is on a wall, but there's two ends and they each have to be connected to something. However, the spring is the agent. The spring is the agent that is exerting a spring force on one of the objects. The objects aren't exerting forces on each other in our model. And so, again, like we described before, if I want to know what the force is on this object, the forces have to be in contact with that object. And so the spring is in contact with that mass, and so I say the spring is an agent, and it exerts a spring force on the mass, which is the object. That spring also exerts a spring force on this other object. Maybe it has a different mass. And if I want to know the forces on this object, there's a spring attached to it, so the spring exerts a spring force on that mass. And so we think of the spring as an agent. Wrong. The poorly drawn end there. The spring is the agent in this context, and it exerts a force on each of the objects that it is attached to. All right. The next condition of our spring force here is that there exists a spring length where it exerts zero force. And I called it before sort of the natural length of the spring. Another word that we want to use to describe that is the spring is in equilibrium. And so there exists a spring length where it exerts a zero force, and we call that length its equilibrium length. Given those conditions, we can now come up with a model for the magnitude and direction of the spring force. The magnitude of the spring force is a constant, and that constant is determined by the individual spring, but it is a constant times the amount the spring is stretched or compressed and when we say stretched or compressed, we mean the amount that the spring is that is the difference in the length of the spring from equilibrium, the amount that the spring is stretched or compressed. The direction of the force, and remember this is a force on one object, whichever one we choose, the direction of the force is the direction the object would move for the spring to return to equilibrium. All right, so let's see what this means here. So let's say I have two masses, M1. They're connected to each other from some spring. And let's say at first this spring is in equilibrium. So this is its natural length. We'll call that L0. And that means the spring is not exerting any force on anything. The spring force it exerts on M1 and M2 is 0. Okay. Now we're going to stretch. I was going to try green. Keep it green here. We're going to stretch the spring. So it is at a new length, L. The amount that the spring is stretched is L minus L naught, its new length, minus the natural length, where it was in equilibrium. All right. So now, given that, what is the spring force that the spring exerts? Well, that if we want a mathematical descriptive representation of that force, we first need a coordinate system, and we need an object on which to understand where that force is. So let's this is one-dimensional. So let's choose the x-axis to be along the one dimension of the spring, and we're going to say that the positive x-axis goes to the right. So what is the spring force? The spring force on mass 1. Okay, so I'll represent that by F sub s. It's a vector, and it's equal to something. Let's get the magnitude first. So the magnitude is a constant that depends on the spring. Fine. And we don't know what that is. We either have to solve for it or we have to be given it, since it depends on the individual spring. That constant is often represented by a k, so that's the constant. And then the other part of the magnitude, it's that constant times the amount the spring is stretched or compressed. And the amount that the string is stretched is L minus L naught. Now the direction of the force is the direction the object would move for the spring to return to equilibrium. So we got to go to our picture. We're looking for the force on M1. And for the spring to return to equilibrium, the mass 1 would have to move to the right, which is the positive x-axis. So the force on M1 is equal to a positive constant times L minus L naught, and it's in the x hat direction, since the spring is a force, since the spring is a vector. All right, now let's look at the spring force on M2. We'll do that over here. Spring force on M2. So, in this case, we have some force. This is on spring 2. If this other one was on mass 2, this other one was on mass 1. This is on mass 2. So the magnitude of the force is equal to a constant that depends on the spring. Well, that's the same constant. The amount that the spring is stretched or compressed, and that's the same as before. It is now, what direction does this force point? Well, it points in the direction that the mass would have to move for the spring to return to equilibrium. Well, that is in that direction. Well, this, given my coordinate system, is the negative I hat direction. So the force on the mass 2 is given by negative x direction, the constant k, times the amount that the spring is stretched. And so in this case, we have a different mathematical representation for each object, but the methodology was the same. We took our spring force, and then given our system and our coordinate system, we were able to come up with a mathematical representation for that force. Okay. Well, I want to, before we leave this, I want to look at sort of a subset of very common spring problems. And I would say most often, one side is attached to something immovable. One side attached to a fixed point, a fixed object, say, or we say a wall, something like that. So for how I might draw a picture of that, instead of the two objects being two masses which move, I might say that one side is a wall, and then the other side is a mass which can move. Now, this is not, a general situation. This is sort of a subset of the general condition, but this allows us to simplify what our mathematical representation looks like. So, in this case, let's say right now that this system is the spring is not exerting a force, so it is at its natural length. We call L naught or something. And now what we'll do is establish a coordinate system where the origin here's my coordinate system, one dimension along the spring, where my origin is at the location of the center of the mass when the spring force is equal to 0. So the origin of coordinate system is at mass location when the force of the spring is equal to 0, or the spring is at its equilibrium length. Now, in this case, we have a very simple mathematical description of our force. So the force, this spring force, is equal to the constant that's associated with the spring, which we call K, and the amount that the spring is stretched or compressed. Well, that amount is now simply x, because if the mass moves to, say, a distance x, that means that the spring is now stretched an amount x. If the system is compressed an amount x, that means the spring is compressed, the length is changed from its equilibrium length an amount x. And so in this case, the spring force has a magnitude which is equal to K times the distance away from the origin, which is just x. And it's negative, meaning the direction of the force always points toward the origin. So we can see this. If the mass is stretched, then the force points to the direction that the mass would move to move it back to equilibrium. Its location is a positive x, but the force then is going to be in the negative x direction. And so that's the reason for the minus. Again, if the system is compressed, so the mass is now at a negative value of x. So this is some negative value of x. The force on the spring is in fact positive. And so in this case, if x is negative, that negative cancels with this negative, giving ourselves a positive force. So our spring force can then be represented by this vector relationship. Now we can note that since this is all one dimension, we can just work with the components of this force. And if we just look at the components, then the spring force, or the x component of the spring force, is just equal to negative the constant K, call the spring constant, times the value of x. Now, this, in fact, might be an expression people have seen for the spring force if they've looked at physics before or taken a physics course, but it's very important to see how limited a case that this particular relationship for the spring force is. This sort of expression only holds when one side of the spring is fixed on an immovable object, where we've established a zero of the coordinate system at the mass when the spring is at its equilibrium length, and we have, say, the x-coordinate system aligned with the direction of the spring, and we're only looking at the x components where the negative sign gives us the direction of the vector, and we've just skipped any of the vector notation. So you don't want to just start throwing f equals minus kx unless you really understand how your particular problem is set up. And just for a final example, let's look at a different coordinate system for this same problem. Instead of having the origin of the coordinate system at the mass, point of the mass when the spring is in its equilibrium position, let's have the origin of the coordinate system look at the be at the wall. In this case, the location of the mass where the spring exerts zero force is some fixed but positive value of x. We'll call that x naught. This is the equilibrium position of the mass, because that is the point where the spring does not exert any force on the mass. Now in this case, the mathematical representation of our spring force is equal to negative k times the displacement x minus x naught along the I hat direction. So again, we have, if the system is displaced further to the positive x, then x minus x naught is a positive number, and it describes the amount that the spring is stretched from equilibrium, multiplied by the spring constant, and it's in the negative x direction because the force is directed in the direction where the mass would move if the spring were to return to equilibrium. Whereas if the system is compressed, then the position of the mass is at a value of x smaller than x naught. So in that case, x minus x naught is negative, and that negative then cancels to the original negative to give us a positive force, which is what happens. There's a positive force that is pushing the mass back to equilibrium. So in a case where the origin here is at the wall, we would have a mathematical representation of the spring force that looks like this. In this case, x naught is the location of the mass at equilibrium. So the spring force, again, we represent as a model. And it's really important to understand everything that goes into the model so that you can then come up with the correct mathematical representation for that force depending on the system that you have, whether it's attached to two masses where both can move, or maybe where you just have one mass attached to a fixed reference point.